Hi there, welcome to today's presentation. My name is Derrick, and today I'll be talking about digital twin knowledge base for submarine robot inspection. First of all, I'd like to talk about my mission, okay? So my goal here is to develop a comprehensive knowledge base for the underwater environment so that the robot can use such a knowledge base to achieve its goals. This knowledge base is supposed to be able to integrate diverse data types. So for example, you have data coming from the camera, the RGB camera, you have data coming from the LiDAR sensors and all other sensors on board the robot. And we want to be able to integrate all of these data types together in one place in the knowledge base. At the end of the day, this knowledge base, through this collective data types, it should be able to provide us some context-aware explanations so that the robot can make sense out of whatever is about to achieve. So given a particular task, the robot should be able to indulge the knowledge base, retrieve some information based on the task, and then use that results to achieve its goals. And we want to be able to achieve some level of real-time capabilities using this knowledge base. So first things first, let's talk about how this kind of knowledge base has been achieved in other scenarios. Taking the kitchen, for example, we have a structured environment. And this structure or this nature of environment is very stable. It rarely changes, so everything is fixed in one place. Secondly, an ontology structure for such an environment will always be fixed and rigid, reason being that things in that environment do not change. And so the knowledge representation is also hierarchical and is also very static. Handling uncertainty in such an environment is very minimal because, again, we have minimal movement of stuff in the environment, and so we don't see a lot of change happening in such an environment. And because of that, to adapt or to update such an ontology or such a knowledge representation, we realize that is very low. Okay? So, we may want to ask ourselves, can we transfer such modeling techniques that happens in a structured environment to a dynamic environment? And the answer is a big no. And the reason is that the dynamic environment, with the rate of change, it keeps evolving each and every single time. Today, a fish should be here. Tomorrow, that same fish should be over there. In a few seconds, there's something moving from one end to the other. So therefore, we want an ontology structure that is flexible, that evolves, okay? And we also want the knowledge representation of that ontology to be contextual. We want it to be adaptable, to be able to change at any point in time. At the same time, we want that same ontology or that same structure to be able to handle some high degree of uncertainty and ambiguity because the rate of change is high in such an environment. In the same way, or the result of it, or at the end of the day, we want that knowledge representation or that ontology in itself to be adaptable, to have some high adaptation in itself. Okay, so let's talk about some challenges that could occur because we've compared the two environments. We have the structured and we have the unstructured. So why can't we apply the structured approach to the unstructured approach? And this is as a result of some of the challenges that comes with underwater inspection or underwater scenarios. One is poor communication, where the robot may not be able to communicate to the mothership easily because GPS and other forms of communication is very minimal underwater. Vision is also very poor because of the nature, the turbidity of the water, how blurry the water may be, how dusty it may be, the marine snow and all other things create a very blurred vision for the robot. So that is also a challenge. And then the last one of it, or last but not the least, is the lack of precise location, because under the water, we are not able to precisely judge where the robot is. One, because of current that drifts the robot off its course over time, and also GPS location doesn't work underwater. Now, yes, there are some ad hoc ways of trying to achieve some of these, trying to solve some of these problems, but these are challenges that exist underwater. And so migrating a modeling technique that was used in a structured environment to unstructured environment becomes difficult. So we want to redefine our problem, because if we want to look at the entire ocean, it's going to be a problem. If we want to model an ontology for the entire ocean, it's going to be a challenge. So we want to redefine the problem to make it, to bring it a step down so that we can get closer to solving the bigger problem as we go. And to narrow it down, we want to look at the subsea station. This subsea station, because we understand where all the machineries are, they provide some level of structure to the environment. The locations of these machines help the robot locate or localize itself in that particular environment. However, we are also not taking away the dynamic nature of the environment, because fishes and flexible cables or flexible pipes will surely be moving from one point to the other. Current will still be in action, so the robot could drift over time, and other forces that could affect the robot could still exist. Now, with this nature of the problem, we can somewhat address the problem of communication, because with a docking station in such an environment, the robot could always dock and then communicate or transfer all data that it has collected in that environment back to the mothership. So yes, in a nutshell, we are redefining the problem or narrowing down the problem to a subsea station. So this subsea station contains jumpers. We can see the AUV. We have wellheads, we have subsea trees and pipelines, and then the manifolds. And this is just an example of how a subsea structure or station or system will look like, and the kind of components it will consist of. So now that we've addressed what our problem is, we've narrowed it down, we want to take a look at a few terminologies. Okay, so what are ontologies? Ontologies in underwater are a structured framework that define the relationship and concept to the domain, such as sensor data, robot behavior, environmental conditions, and mission objectives. Okay, in a nutshell, they represent the concepts or the classes of that particular domain, in our case, underwater domain. Okay, or to narrow it down to the problem that we have now, to the subsea station. So we are talking about ontologies about subsea stations, right? And they represent key elements in that environment. So like marine species, environmental conditions, all these components of robots are mapped or translated in this ontological structure. Now, these ontologies, they help support reasoning capabilities, and they also help inform, they help robots make informed decisions because of their contextual nature. They help the robots make informed decisions based on the missions they are trying to achieve. And in a nutshell, they help organize and structure tasks such as navigation, exploration, and mapping, ensuring that robots understand and execute complex underwater missions efficiently. So here's an example of how an ontology will look like in this case. We can see that on the top image, we have the robot, which is defined in the ontology with various attributes. And here we have the AUV, REMARO AUV, and it has an ID. It has other attributes called infield, at object, distance from object, with other information. In that same image, we can see that we have another information about the machine in there. And this machine, the tree's name is XT3. It also has ID, where in the field it's located, and so on and so forth. Now, all this information are stored in the knowledge base, but this structure here is the ontology. Okay, is the ontology that we have in this case. All right, now we've talked about the ontologies. Now let's look at another key or another important topic in this presentation that we are trying to do, and that is a digital twin. In this case, a digital twin in underwater is just a virtual replication of the physical underwater robot, its component, and an environment as a whole. Okay. Now, digital twin helps in real-time monitoring, because with the virtual environment, we are collecting sensor data from the real environment into the virtual environment and then remodeling it to test out other ways of accomplishing certain missions. And if we tweak certain data parameters, what are some of the informations we could get out of it, or what results could we get out of such tweaks? Now, digital twin can be used to optimize mission plans. And like I said earlier, by simulating a mission before the robot achieve or before the robot departs, we are able to help the robots collect enough information about how to handle the task ahead. So, if we combine ontologies, knowledge representation and reasoning, and digital twin, if we combine these two concepts together, we arrive at another concept called the semantic digital twin. And what's the semantic digital twin? Well, it's basically combining all the good and benefits of ontologies and the digital twin and creating a bigger benefit for underwater scenarios. So in this case, the semantic digital twin just extends the concept of digital twin by incorporating the meaningful context through structured knowledge, enabling deeper interpretation of the robot's data and interactions. The semantic digital twin further helps the robot make smarter decisions, such as adapting its behavior based on environmental changes. So for example, if the turbidity of the water is too high, the robot should be able to detect and understand that, okay, at this point, this mission will not be possible, so I need to abort. Okay. The next thing is the semantic digital twin can dynamically adjust mission objective based on evolving understanding of the environment. So with the ontologies or the semantic part of the digital twin, we are able to then develop contextual understanding of whatever is happening in the environment. And this time around, it goes beyond just monitoring, it goes beyond just collecting data, but it goes to the extent of analyzing the data and coming up with meaningful ideas or meaningful approach of trying to resolve problems in this environment. So, what have I done so far in this to achieve my goals? So currently we have a knowledge base that has been extended. We collected a few knowledge bases available for subsea stations, oil and gas platforms, and we've extended it to achieve what our goal is. Secondly, we also have a digital twin in an Unreal Engine, and the reason for using Unreal is because of its realistic graphics. We are able to simulate realistic nature of the environment so that we can have some level of understanding, or we can build some level of ontology structure around this realistic virtual environment. Now, through data analysis, we are able to also make some inferences. So when we apply the reasoner to the knowledge base is able to make some references that wasn't already in the knowledge base. And to make it easier for use, we've provided some interactions using an endpoint for now. And however, we could also interact with the knowledge base through a terminal endpoint. So this is an example of the ontology that we have, and one of them, the sample one that we see on the screen is an ontological structure of the manifold, and we can see that this is written in R. And I'm not going to bore you throughout how this is structured. However, but I'll just highlight a few things. We can see that using the URIs, we are able to map our individual or instance to the classes that are existed or that exist in the terminological and ontologies or terminological box of underwater. And with this particular one, we can see that it has some properties like component of, and we can see that this manifold base is a component of manifold in itself, right? So that means that this ontological structure defines how the manifold is. This is also a sample query to retrieve all the it's basically trying to look for all the flow lines that can be inspected, and then based on that the robot can then perform an action. And using the terminal or using the endpoint, we can retrieve all the flow lines that can be inspected at this particular instance. So, in a nutshell, my goal is to be able to develop a knowledge base for underwater environment, and my approach here is to develop a semantic digital twin for such an environment because of its contextual nature. It's able to provide us feature-rich knowledge base or feature-rich information that the robot can use to achieve its goals. Using the bare digital twin, and it may not give us all the information because the digital twin just monitors, collects the data, and then recreates it and then monitors the environment. However, taking it a step further and applying the ontologies on top of it makes it much smarter. So this is an ongoing project, and hopefully we'll be able to give an update on this in the near future. Thank you for listening. Once again, my name is Derrick Odonko, and I'll see you on the next one. Bye.